Hello everybody, my name is Kiran. I am working as an assistant professor in the department of EEE Anits. I welcome you all to my 6th lecture on the concept of time response of control system. In my first lecture, I discussed what is time response, what is steady state and transient state responses, and what are the various standard test inputs, that is ramp, step and parabolic inputs. We have derived the expression for steady state error and on what factors does this steady state error depend on and their corresponding effects. In the second lecture, we have seen various tutorials based on error coefficients, that is Kp, Kv and Ka, and their corresponding steady state error for step, ramp and parabolic inputs. In third lecture, we have derived expression for time response of first order as well as second order control system. For first order control system, we have taken 3 cases, that is for step input, step ramp input as well as parabolic inputs. For second order control system, we have taken 4 cases, that is for underdamped, undamped, overdamped and critically damped cases. Here for second order we have considered only unit step input. In fourth lecture we have derived the expression for various time domain specifications, that is rise time, peak overshoot and settling time. In my previous 5th lecture we have seen some tutorials based on second order control system, and in today's lecture also we are going to continue some more tutorials based on second order control system. We are given that for a unity feedback system, the open loop transfer function is K by S into 1 plus St. For peak overshoot, when it reduces from 0.6 to 0.2, and this is only due to change in K. So we are asked to find, or we are asked to prove that Tk1 minus 1 divided by Tk2 minus 1 is equal to 43.33, where K1 is the value of K when peak overshoot is 0.6 and K2 is the value of K when peak overshoot is 0.2. Since we know the open loop transfer function, we know the expression for closed loop transfer function, that is g of s by 1 plus g of s into h of s. For unity feedback system, h of s value is 1. That will give me k by t by s square plus 1 by t into s plus k by t. Comparing this with my standard form, omega n square will be k by t and 2 zeta omega n will be 1 by t. So upon equating these two relations, that will give me omega n as root over k by t and 2 zeta omega n as 1 by t. So in this, if I substitute this omega n in place of omega n, if I substitute root over k by t, that will give me the value of zeta as 1 by 2 into root over kt. So let us now take 2 cases individually, when peak overshoot is 0.6 and the second case when peak overshoot is 0.2. So when peak overshoot is 0.6, let me assume that the damping ratio is zeta 1. So we know the formula for peak overshoot, it is e power minus pi zeta by root over 1 minus zeta square. Since in the first case we have assumed zeta as zeta 1, so 0.6 is equal to e power minus pi zeta 1 divided by root over 1 minus zeta square. So taking natural logarithm on both sides, that will give me the value of zeta 1 to be 0.1602. So the second case, for MP is equal to 0.2. I will assume the damping ratio to be zeta 2. Again equating according to the formula, 0.2 is equal to e power minus pi zeta 2 divided by root over 1 minus zeta 2 square. Taking natural logarithms on both sides, and that will give me the value of zeta 2 to be 0.4559. So we have obtained the value of damping ratio in both the cases. Okay, so in first case we have obtained zeta 1 as 0.1602. In that case, k value is equal to k1, which is given already in the question. Okay, so next, using that relation zeta 2 when it is 0.444559, which I have obtained, k value is nothing but k2. So both values are given in the given tutorial. Okay, so the relation that we got earlier, so using that relation, zeta is equal to, if I take you to the previous screen, here zeta I have obtained as 1 divided by 2 into root over kt. Okay, so using that relation now, for first case, since zeta is nothing but zeta 1 and k is nothing but k1, so zeta 1 will be 1 by 2 into root over k1 into t. That we have obtained as 0.1602. So if I cross multiply, and which will give me, because in this case I need to find the ratio tk1 minus 1 by tk2 minus 1. Okay, so from this I will find the value of tk1 as 9.7412. okay, we cross multiply this and just squaring on both sides, that will give me the value of tk1. Since we need tk1 minus 1, so that will give me tk1 minus 1 value as 8.7412. Similarly, for second case, when MP is 0.2, zeta 2 is 1 by 2 into root over k2 into t. That we have obtained as 0.4559. So that also, on cross multiplying and squaring on both sides, will give me the value of tk2 as 1.2028. Since I need the value of tk2 by minus 1, that will give me the value as 0.2028. So taking the ratio of tk1 minus 1 by tk2 minus 1, which will give me 43.33. So hence we have proved that tk1 minus 1 by tk2 minus 1 is equal to 43.33. The next tutorial, the measurements conducted on a control system show the output response of the system as 1 plus 0.2 into e power minus 60t minus 1.2 into e power minus 10t when it is subjected to unit step input. Obtain the expression for closed loop transfer function. Also find damping ratio and natural frequency. Since we know the expression of time output response in time domain, applying Laplace on both sides. So C of t is C of s, Laplace transform of 1 is 1 by s, Laplace transform of e power minus 60t is 1 by s plus a. We know the formula. Laplace of e power minus at is 1 by s plus a. In place of a I have 60, and since I have 0.2 before, so taking Laplace I will get 0.2 divided by s plus 60. The third term, it is e power minus 10t, so the Laplace will be 1 by s plus 10. So minus 1 by 2 divided by s plus 10. So after knowing the expression of C of s, R of s is given, isn't it? Since it is unit step input, it is 1 by s. So here taking the ratio of C of s by R of s, which is nothing but the Laplace transform of a closed loop control system. So dividing by R of s, which will give me the expression as shown, s into this entire expression which I got earlier. So we know that this s and this s will get cancelled in the first term, and both second term and third term will get the s term in the numerator. So this is the expression of Laplace, the closed loop transfer function, 1 plus 0.2s by s plus 60 minus 1.2 into s by s plus 10. So if I take LCM and find out the simplified closed loop transfer function, that will give me 600 divided by s square plus 70s plus 600. So this is after if I go to the previous slide. So if I multiply everything in the numerator as well as in the denominator, after simplification, this is the expression that I'll get for closed loop transfer function. Now comparing this with my standard form, that is omega n square by s square plus 2 zeta omega ns plus omega n square. Omega n square will be 600, 2 zeta omega n will be 70. So upon equating these two, that will give me the value of omega n as 24.49 radians per second and zeta value as 1.42. So here this damping ratio value we have found, zeta, natural frequency also we have found. We also finished the finding the expression for closed loop transfer function. So the next tutorial, for a given block diagram control system, we are asked to find what is the value of K and Kt such that the damping ratio is 0.6 and settling time is 0.1 seconds. Given that the settling time is 3.2 by zeta omega n, and asks us to assume that it is unit step input. Okay. First, let us find the transfer function using block diagram reduction technique. Then we can get the values of K and Kt. So we know the block diagram reduction technique. We have already discussed this in my previous lecture on block diagram reduction technique. You can check it out later. So using block diagram reduction technique, this firstly, this is eliminating feedback rule. So if this is G and if this is H, we know the formula. Upon eliminating feedback loop, the formula is G by 1 plus G into H, isn't it? So here in place of G I have 100 by 1 plus 0.2 into S, and in place of H I have Kt. So I assume that is on G1 of S. So upon taking LCM and simplifying, that will give me the expression of G1 of S as 100 by 1 plus 0.2 S plus 100 Kt. So then this will be in cascade with K and 1 by 20S. Okay, so these three blocks will be in cascade. So that is why just we need to multiply. So that is why I multiplied K by 20S. So this is my open loop transfer function. So if I simplify, that will give me the open loop transfer function G of S as 5K by S into 1 plus 0.2 S plus 100 Kt. Since feedback here value is 1, so using the closed loop transfer function formula, C of S by R of S is nothing but 5K by 0.2 S square plus S into 1 plus 100 Kt plus 5K. So that will give me the standard form. So in order to compare, let me go to my previous slide. If I want to compare this with my standard form, the coefficient of s square should be 1, isn't it? So again, if I divide by 0.2, that will give me my closed loop transfer function as 25k by s square plus 5s into 1 plus 100 kt plus 25k. So comparing this with my standard form, it will give me omega n square as 25k and 2 zeta omega n as 5 into 1 plus 100 kt. So we are already given zeta as 0.6, already given that the settling time is 0.1. So 3.2 divided by zeta omega n is given as 0.1. So if I substitute the value of zeta in the expression of settling time, that will give me the value of natural frequency as 53.33 radians per second. So that is what we have obtained, and this I will equate to 5 into root k, because from here omega n square is nothing but 25k. So that will give me omega n as 5 into root k. So equating this value to 5 into root k will give me the value of k as 113.78. Next, the second part we have obtained as 2 zeta omega n as 5 into 1 plus 100 into kt. We already know the value of zeta as 0.6 and the value of omega n is 53.33. So now upon substitution, that will give me the value of kt as 0.118. So I found both the values of k as well as kt for the given data for the given block diagram of a control system. The next next tutorial, he has asked us to find the value of k as well as k2 such that MP is 0.2 and TP is 1 second. That is assuming it is unit step input. Also we need to find the expression for the rise time and settling time values also. So again, using block diagram reduction technique, we need to find the value of closed loop transfer function. In place of g of s, I have k by s into s plus 1. In place of h of s, I have 1 plus k2 into s, which will give me the expression of closed loop transfer function as k by s square plus 1 plus k into k2 into s plus k. Comparing this with my standard form, omega n will be root k, 2 zeta omega n will be 1 plus k into k2. So from that I will get the expression of damping ratio zeta as 1 plus k into k2 by 2 into root k. So now utilizing the given data, the peak overshoot is given as 0.2. We know the formula, it is e power minus pi zeta by root over 1 minus zeta square. Okay, so taking natural logarithms on both sides, from that I will get the value of damping ratio. So here after applying the natural logarithms, we again need to cross multiply and square on both sides. That will lead my damping ratio value to be 0.456. Next, also peak time is given as 1 second. We know the formula, it is pi by omega d, that is nothing but pi by omega n into root over 1 minus zeta square. Just now we have already found the value of zeta as 0.456. Substituting in that will give me the value of our natural frequency omega n to be 3.53 radians per second. So now after finding the value of zeta and omega n, now we need to find the value of rise time and settling time. We know the values for the expression for rise time and settling time, isn't it? So before that we need to find the value of k and k2. Okay, so we have obtained this relation previously. We have found out the value of omega n as well as zeta. So from that, if I substitute, that will give me the value of k as 12.45, and from the second expression, if I substitute, that will give me the value of k2 as 0.17. So now, after getting the values of k and k2 as well as zeta and omega n, now we need to find the values of rise time as well as settling time. We know the expression for rise time and settling time. So rise time, the formula is pi minus theta by omega d, where theta is tan inverse of root over 1 minus zeta square by zeta. So if I substitute the value of zeta, that will give me the value of theta in degrees as 62.87. So if that I multiply by pi by 180, that will give me the value of theta in radians, that is 1.097 radians. So this, when I substitute this here, that will give me the value of rise time as 0.65 seconds. So settling time, the formula we know that it is 4 by zeta omega n. Zeta value we know, the value of omega n also we know. Upon substitution, that will give me the value of settling time as 2.48 seconds. So in my next tutorial, a step response of a second order system is given for an input of 2 into u of t. We need to determine what is the open loop and closed loop transfer function for unity feedback system. So it is very obvious that this time period is the time at which you are getting a peak overshoot. So that indicates that the peak time is 2 seconds, and peak overshoot can be calculated from the diagram, from the graph that is given as 2.5, which is the peak value, divided minus 2 divided by 2 into 100. That will give me the peak overshoot as 25%. But we know the formula, it is e power minus pi zeta by root over 1 minus zeta square. So applying natural logarithms on both sides, cross multiplying, squaring on both sides, that will give me the value of zeta as 0.40. Next, also we know that the peak time is 2 seconds. The formula is pi by omega n into root over minus zeta square. So if I substitute this value of zeta in this formula, that will give me the value of natural frequency omega n as 1.71 radians per second. So next we need to find the expression for open loop and closed loop transfer function. So closed loop transfer function, C of s by R of s is nothing but G of s by 1 plus G of s into H of s, and in the standard form its formula is omega n squared by s squared plus 2 zeta omega ns plus omega n squared. We know the values of zeta, we know the value of omega n. So upon substitution, that will give me the expression for closed loop transfer function as 2.94 by s squared plus 1.38 s plus 2.94. So this we know that it is G of s by 1 plus G of s into H of s. So H of s is nothing but 1 because it is given as unity feedback. This term I can rewrite as s into s plus 1.38. Okay, so since H of s value is 1, this expression can be written as G of s by 1 plus G of s, and cross multiplying, that will give me the expression for open loop transfer function G of s to be 2.94 by s into s plus 1.38. So the next tutorial, the system G of s is 15 by s plus 1 into s plus 3. H of s value is 1. It has asked us to determine the characteristic equation omega n and zeta, time period of oscillation, and number of cycles the output will perform before settling time. So this will be, I think, the last tutorial for this video lecture. So we know the formula for characteristic equation, that is 1 plus g of s into h of s is equal to 1. So before that, we need to first find the closed loop transfer function g of s by 1 plus g of s into h of s, which will give me 15 by s square plus 4s plus 18. This is not in the standard form, so we need to consider omega n square as 18 only. So anyhow, the characteristic equation is the denominator polynomial, that is s square plus 4s plus 18 is equal to 0. Next, comparing this with the standard form, omega n will give me 4.24 radians per second, and zeta value, damping ratio, will get as 0.47. Next, we need to find the time period of the oscillation. So t is equal to 2 pi by omega d, where omega d is omega n into root over 1 minus zeta square. We know the value of omega n, we know the value of zeta. So upon substitution, that will give me the time period of oscillation as 1.67 seconds. The settling time, Ts, we know the formula is 4 by zeta omega n, which is 2 seconds. So now we need to find the number of cycles output will perform before settling down. So for one cycle, we have got 1.67 seconds. So how many cycles we need for the output to perform in 2 seconds? So that we can calculate as 2 divided by 1.67. That is nothing but 1.19. So this ends my today's lecture on the tutorial of second order control system. So in the next lecture, we are going to see the importance of various controllers that we use in our control system, that is P proportional controller, integral controller, derivative controller, and also the combination PI, PID controller. In detail, we are going to see what is the effect of proportional, integral and derivative controllers also. And if time permits, we are also going to see some of the tutorials based on the PID controllers. Thank you.